guys know where the rest of the guy goes?
Maybe because we've been starting at 12. Maybe they're thinking it starts at 12.
You guys, when you guys log into D2L, even like this morning to do the exam, you never looking on the news on the first page.
Well, 38 of or 37 of us did.
Yeah. So, most of you guys, you are here, and when you are here, that's a good thing. Okay, I gave those guys a few minutes, but there's a few guys I want to. Oh, I already tortured the guy's name called Ethan, right? No, sorry, Ethan. Ethan, he failed automatic control by Asian standard. He didn't real fail the exam down here, but I like to torture him. Okay, next one, Hayden. Hayden's here, right? No, I didn't give him the version F test. I tried to be nice to him, but
it felt like the version F test, Jack.
Hayden, you are in my class. You answer question, you always get it right. What happened during the exam time?
I don't know. I bombed it hard. I did the same thing on this last one, Jack. I don't know what's like. Do we have the technology to like check them? Because I am curious where I'm going wrong with some of the stuff. Like, even
yeah, I
like
look at your exam for automatic controls.
Yeah.
Some of the thing I talked in the class, did you write down the notes or did you even
Yeah,
make
I did.
notes?
I was paying the most. I took pictures. I got it all. I don't know where I went wrong. Was just like
So when you answer the question, how you get those questions wrong?
I don't know.
I will pick an easy question.
Okay.
I hope you're okay. Don't mind I torture you down here, right?
Yeah, I'm okay with that. I'll just, you know, I'm hoping to do
one of the questions on there, it's they said compare open loop system and a closed loop control system.
Yeah.
They give you a few choice. Less costly, more difficult to calibrate, require feedback, and all above, right? We said that what's the main thing between closed loop and open loop? Automatic control.
And what did I put?
Yeah, you put a more difficult to calibrate.
Okay.
Most people get that question right because I think I told you guys in the class. I said the major difference is between open loop, closed loop is the feedback. How can you choose something so funny, more difficult to calibrate? Do I ever told you how to do the calibration?
I guess I was just thinking that because of the automatic controls that there was more calibration with the closed loop system. Like you had to, because yeah, that was one of the things that it was required more work and maintenance and like automation.
We did talk about how it's a lot more complex, so I could see why you would think that it would be more difficult to calibrate as well.
Yeah, that's where I think I must be just like, because I know I'm getting anxious too during these tests, but I'm wondering if my mind's just scrambling up words like I'm reading them wrong or something. Like, yeah, I can see where I went with that. Like closed loop systems are more
no excuse accepted.
Okay.
And you got a few calculation questions wrong.
Okay.
How can you do that?
I don't know, Jack.
You don't know?
No.
Send me your home address. I'm gonna come and give you a private tutoring.
Okay.
Okay.
I will send it to you.
Another question, they ask you to select a output transducer. They give you string gauge, thermistor, RTD, and the infrared LEDs.
Oh yeah, I knew I messed that one up. But unfortunately I'd already.
Yeah, there's no unfortunately. Okay.
Okay.
You gotta do some kind of punishment. Either if you're married, ask your wife or your kids to do it. If you're not married, ask your parents to do it.
Okay.
Okay.
Someone to put me into shape.
Yeah. Someone need to put you into the shape.
Okay.
Okay. It's 44. We only have 40 students here. So whoever not here, they have to get this information from whoever. Okay, so I try to show you a few things for this renewable energy exam. I'm gonna share my screen with you. Hope you didn't see the exam question. So here the course homepage, right? Whenever a new topic come up, we have some kind of news for you. So you guys probably get the link down here, get into my class. That's great. In this renewable energy, I opened everything. So first, you will have a 4 score learning topic. Those are online learning material, like a wind power, photovoltaic, PV module, solar thermal. Those 4 score learning topic will give you the material you require. You can see in here, you have quizzes for renewable energy system. So these quizzes down here, if you go in there, oops, shouldn't be say this page. So here is your renewable energy quizzes. So if I go preview, that's what you're gonna see. They will give you 10 questions, ask you to try. The quiz bank for this renewable energy system, it's have I think it's about 100, maybe 120 to 150 questions. And all those quiz is related to those 4 score learning topic. So those one, you're gonna do them yourself. You click on them, they will pop up a new window. They will bring you to go through a bunch of pages. So that's your score learning topic. And then I have the PDF file. The PDF file, wind power, photovoltaic, geothermal, hydrokinetic, and micro hydro, solar thermal, hydrogen fuel cell. So here's the one updated one, probably have more things. So that's why that one is hiding. The hydrogen fuel cell updated. So we're talking about 7 topics: wind power, photovoltaic, geothermal, hydrokinetic, and micro hydro, solar thermal, and hydrogen. That's all renewable energy system. Those are the PDF version of the PowerPoint I'm gonna go through in the class. So we will start on wind power. Tomorrow morning we will start on geothermal. Then if we have extra time, we will go through the solar thermal. Then we probably will go photovoltaic. Then the last one, next week we go hydrokinetic, micro hydro, hydrogen fuel cell. Also, I gave you one document down here. It's called BC Hydros. They call it's a BC Hydro Connect distributed generation interconnect requirement. So any type of renewable energy system, or even if not renewable energy system, you have a backup generator, you want to connect onto the BC Hydro's grid line, you have to match in the requirement down here. So I give you this PDF file. It's about how many pages? I think 30, 40 pages. They have a bunch of requirements in there. I will find a time to, in the class, to go through several important points in this document. Okay, and you can have a different ways. One way is to print this document out if you have a printer and you prefer to read the paper version. Another way is you can always download this document, right, as a PDF file. Then depends on your either what type of the software you got. You can because why I try to say this is you will have a few questions came from that document as the exam question. So you need to know certain thing in there. If you have a, let's say you have a software, you can highlight those PDF file, that's great. If your software, you cannot do anything, you can just read it. You have to find a way to, if you want to, like I'm gonna open my document down here. I will just show you example down here. So my document down here, I have a bunch of things highlighted. When I go through them, I probably just gonna go through those highlight items with you. Once, I think the last term, no, the first term, from January to March, that term, one student asked me, he said, hey, Jack, you gave us a PDF file, wasn't have any highlighting inside. Can you give us the highlighted version? I said, no. Because you're supposed to read the document, you're supposed to highlight your own document yourself. That will be few questions came from that document. So the exam gonna be like this. Total is 50 questions. 8 of the question, 8 questions is from the online quiz. So 50 questions, that's 8 questions from that online quiz. The bank is about 120 to 150 questions total in there. So to do those online quiz, you can try yourself, or you can go through that full SCORM learning object on the D2L. Then we have about let's see, about 4 to 5 questions is based on your previous year knowledge. So when I say previous year knowledge is here I give you an example. If I give you a 3-phase generator, it's rated, let's say 60 kVA, and your supply is 600. The generator got 600 volts. Can you find out what's the rated current for this generator? You better know it, right? So got a 60 kVA divided by 600 volts. You need a rule 3 down there, right? Yeah, if you forgot the rule 3, then you're gonna be in trouble. Then probably something related to your code. So if you find the rate current, and if you have, let's say, whatever the current we got here, 60 kVA. So you got a current about 57.74 amps. And for that current, if I want to find out, okay, the code we might have something that you have to, the ampacity of the conductor have to be, ampacity of the conductor have to be 125%. So you're gonna do 125%. So give you 72.17 amps. Then you got to be able to use your code book, let's say table 2, to find out what size, maybe TWN75 or RW90 conductor for that. So those type of things, because you learned this in third year, you learned to find this one in your code book, you learned in your all 3 years before. I might throw 1 or 2 questions on the working sheet that will be this type of question. And during the class, I might throw a question down there, ask you to do it. But those things, you're supposed to know them before. So there's about 4 or 5 questions is, or another way, just like I think Justin asked me a few minutes before. I didn't teach you in the class. I probably not gonna go through the code book to teach you all those, but that will be question like that on your exam. You need to know how to do them. A smaller portion, not a big portion. If you don't know them, not gonna be just because you can't do that few questions, you're gonna fail. That's is a type of question you're gonna encounter. So that gave us, let's say, already add up to 12 or 13 questions. Then we have about another 37, 38 questions. Those 37, 38 questions, you will have about let's say 32-ish, 32 to 33 questions. You can find the answer in the PDF file for PowerPoint, or you can find the answer in the working sheet. So that will be a few questions down. That will be about 32 to 33 questions in that portion. And there will be another 4, 5 questions. You're not gonna find anything in there, but I'm gonna show you in class. So if you follow me in the class, I will show you there's certain thing, how to do them, what's that, and then you will know them. But if you didn't show up in my class, yeah, sorry, I can't help you. So Hayden, you better improve your mark on this one, otherwise someone gonna getting hurt really bad.
I will.
Okay. Is that fair? Everyone understand what you're gonna say on these topics exam? It's not gonna be 150 minutes. It's about 120 minutes for the exam, and it's a 50 question. But I would think you probably only have less than 8 question is a calculation. Most question is a basic things. So multiple choice, true or false. And from the automatic control topic, you guys can see, if you follow me around the class, did I told you most question on the exam? Okay, you guys are all quiet, no problem. Let's put it this way. For automatic controls, I saw people got a pretty high mark, right? And 4 people got 100%. For this one, it will be little bit tough to get 100% because it's a wide range of topic, and I picked the question from all different place. Yeah, it's not Yifan. You already know that, right? Oh, you guys want to know who got 100% on the exam? Yeah, Yifan, because I know you before, so that's why I can make a joke with you. I hope you don't mind. The working sheet is here. So here's a bunch of working sheet, and the working sheet have answers in there. So you can check the answer, or if you really don't know how to get those answers, come to the class to ask me. That's good. Your feelings hurt? You want a hurt feeling report? I can send you one. You can fill them out. Okay, so I know you guys just had the exam this morning. We're not gonna go crazy hard this afternoon. We're going to be just get into this topic. Before I start, you guys are okay with what's going to be on your exam so far?
Yeah.
Okay, and you guys have an idea what you need to learn. I can tell you, my last class, there's a people, he got a pretty high mark. He did all this part right, but he mixed a few questions from the online quiz. The online quiz is actually pretty easy question. So he didn't get to 90 because he asked me, he said, oh, why my mark is didn't high enough? I checked and said, oh, all your question get wrong is from online quizzes. So it depends. You have a goal you want to achieve, and you have the time you're available. You got to be able to somehow to manage those things most cost effective, right? To achieve your goal in this course. So another way is if you do all the online quiz, if you do all the working sheets, you probably will pass this topic no problem. But if you want to get a high mark, you got to working a little bit hard. Okay, we're going to start this topic. We only have 44 people. So if they are late or they don't want to join my class, then no problem. Okay, so renewable energy, you guys all know it's a kind of more and more popular down here because we want to be more environmental friendly. We want to save the earth. We don't want to cause so many pollution. So now we focus on more renewable energy. The renewable energy is the energy can derived from a resource naturally replenishable. Yeah, if you are a warrior or you are a man or you are a person, a grow-up person, an adult, you shouldn't be crying over something you cannot change, right? You have to put your effort into the new topic. So here gave you a bunch of things. Sunlight, it's always there, and it's replenishable, so it's considered renewable energy. So we can use the sunlight. We're talking about solar thermal for heating, for generating electricity. We can use the solar photovoltaic. We can have the generate electricity, wind power. That's the wind turbine, wind power generator, water, like a hydro generator is one of them. But usually building big hydro dam, they consider you're gonna flood lots of area, cause the environmental impact. So there's a different way, like a micro hydro. You just need to put a smaller water pipe, have a little bit of difference between the water level, and we can also use they call the hydrokinetic. If you put some type of a generator in the river, in the ocean, you don't have to build a dam or something. They can, by the current flow, pushing the turbine to generate electricity. So that's water ties. And geothermal is the Earth, internally of the Earth is at a pretty high temperature. We can use those heat from the internally. We can use them if you have a volcano activity or you have a hot spring. We can use those water or steam to generate electricity. But for normal use anywhere, because below the Earth's surface, at a certain depth, usually depends on the book, sometimes say 5 meters, sometimes say 15 meters, the temperature below Earth's surface is always constant. So some of you been seeing those heat pump, right? Mostly you saw is a air source heat pump. But if the air source heat pump have some disadvantages because in the summer, you try to cool your house down, the outside temperatures are already so high, and you try to dissipate the heat from inside to the outside, and it make the heat pump working harder. In the winter, the outside temperature is so low, but you try to heat your house up, so you try to extract the heat from the outside. It's also kind of difficult. But geothermal, because those things under the Earth's surface, the pipe, everything buried under Earth, and at that depth of where they bury the pipe, the temperature is constant, keep between 10 to 12 degrees. So it's much easier for you exchange either the heat or thermal energy with the ground or earth than with the air. So those are all considered renewable energy source. And you will have one question came from here. So a multiple choice question will ask you which of the following is not considered as a renewable energy system. what do you think if I have a petroleum oil? Is that a renewable energy source?
No.
No, good. Or another one we call, is the natural gas considered a renewable energy source?
Also no.
Yeah, so your answer right. Natural gas is not a renewable energy, okay? Hope you don't get that one wrong on the exam.
Loud and clear, Jack.
Okay. So if you get this one wrong on the exam, someone gonna come to your house to teach you a lesson. One more thing is called a fuel cell. The fuel cell is actually, we still have to find a way to generate a hydrogen fuel, but the hydrogen fuel is easy to get because we can just put in some kind of use electricity, DC electricity, to put into the water. We can separate the hydrogen from the oxygen. So the benefit with the fuel cell is when you combine the hydrogen and the oxygen together, they will generate electricity, they will generate heat, and the end product is only water. So there's no pollution to the earth or anything. When we're talking about renewable, it's we can replenish those energy very quick. So if it take a million years or even hundreds of years, we don't consider that's renewable energy. Okay, that's okay. Yeah, don't make that one wrong. So here's a few different type of, they give you the picture. This is smaller wind turbine. Usually you can install in a farm or in your house if you have large lands. Those large wind turbine usually is by those utility company or some electrical company. They will build lots. This is hydrokinetic. They put those turbine under the water by the ocean or river current. They will push the turbine to generate electricity. This is micro hydro. If you have a creek or have a smaller river run down from the mountain or hillside, you can use those water to generate electricity. This is a table pretty early, but they consider the renewable energy consumption gonna increase and the generation gonna increase. The old style like the coal or the oil, the gas, they're gonna drop because those things once is they take a millions years to be created, and we cannot wait a million years to have the new oil, gas, or coal for our energy requirement. And it's the government putting incentive down there, and lots of company doing investment, and we as electrician is become more and more popular down here. Renewable energy didn't take too much percentage before, but now it's more and more. Now I will show you some, because the first topic we're talking about the wind turbine, so I'm going to show you a few YouTube videos. First one is we're talking about how a wind turbine works. So that might be, I think, something you need to know. Okay. So that's one video. One video show you some basic thing about the wind turbine, and I got another video I'd like to watch a little bit. Then I'm gonna ask you a question.
L100 wind turbine is the flagship model in the latest generation of wind turbines by Lachave Wind. Equipped with the latest technologies, including Lachave's own direct drive generator, this turbine is ready for the future. Cost reduction and simplicity were the drivers in the development of this multi-megawatt wind turbine. With more than 35 years of experience and more than 1,200 wind turbines installed worldwide, Lachave builds upon great expertise. The L100 generator is therefore built completely by in-house engineers. After 8 months of producing and purchasing parts, the entire turbine can be installed on location in no less than 15 days. The great list of key features of the L100 with 135 meters hub height starts with the foundation. Because of the large tower diameter at the bottom and its resulting efficient force distribution, the foundation can be kept relatively small. This mainly saves a lot of concrete and rebar, but also serves to provide an elegant integration into the landscape. The 135-meter-high tower is constructed with steel plates. Not only does this provide high stiffness, it also serves for easy installation. A conventional concrete tower would need up to 200 truckloads of concrete slabs. This steel tower is brought onto the location in no more than 19 frames with steel plates. This high efficiency brings great cost reduction. This cost reduction even continues after its operational period. A conventional concrete tower usually requires expensive demolition and disposal, whereas a steel tower can easily be deconstructed and recycled. This means a significantly higher salvage value. After climbing the external stairs, you will find yourself on the tower base platform. This is where the grid inverters are situated. These devices convert the alternating current with random frequency into alternating current with a fixed frequency so that it can be transported to the main power grid. These grid inverters are a standard product by ABB, an internationally acclaimed producer of high-grade electronics. On this level, you will also find a control panel. This device displays real-time settings, technical data, and performance data. Thanks to the hollow tower, all maintenance can be performed from within the structure. To perform maintenance on the nacelle or one of its components, service personnel can easily go up with the service elevator. The elevator uses the emergency stairs to climb up the entire length of the tower. This saves valuable space and provides great stability. In case of an emergency, personnel can still use the ladder and climb through the elevator's retractable floor and roof. An important safety feature. After a ride of approximately 8 minutes, plus a short climb, you are on the highest platform. This is where the yaw bearing is continually lubricated with an automatic lubrication system. The grease overflow containers ensure a clean and optimal operation. One level higher and you will be in the nacelle. The nacelle can be kept very compact thanks to the design of the direct drive generator. There is no big gearbox, complicated cooling system, or high-voltage power transformer in this nacelle. Just 6 very reliable yaw motors which constantly turn the nacelle with its rotor facing the wind. These motors also deal with the great forces the rotor has to endure due to the turbulent wind. A control panel, much like the one downstairs, takes care of accurately displaying parameters and statistics, as well as providing control of vital operating functions during maintenance. The main bearing, in which the entire rotor and generator are mounted, is a custom design on which a lot of attention has been spent. Years of experience have brought the engineers to an optimal design of 2 lubricated bearings inside a single housing. This design provides excellent force distribution, correct lubrication, and a long lifespan. The most important component of the turbine is held by the main bearing, the generator. The rotor is directly mounted onto the generator, automatically synchronizing the speed of both devices. The generator is completely sealed from its environment. This makes it withstand extreme conditions, and thanks to the lack of a gearbox and accompanying oil lubrication system, this generator easily handles very cold weather conditions. The relatively small energy losses, which is made possible through its very efficient design, are converted into heat. This heat is efficiently dissipated to the outside air through the cooling fins around the perimeter of the generator. More wind means more power, with a part heat. More wind also provides better heat dissipation through the fins. These processes go together. It ensures reliable and constant operating temperatures. The front section of the hub houses the electronic blade pitch control system. One AC motor per blade constantly controls the pitch to ensure optimal production at all wind speeds. A DC motor with battery serves as a backup. These motors can turn the blade into a safe position in case of a power outage. The status of the batteries and safety system is closely monitored by the central computer. Safety first. Lightning strikes are a realistic risk factor for structures this high. That's why the entire nacelle is surrounded by a Faraday cage. This provides extra protection for internal components and service personnel in case of a lightning strike. The blades are equipped with lightning conductors that safely guide the lightning through the foundation into the ground without causing any significant damage to the components. Lightning rods are mounted on top of the nacelle to protect the important wind direction and wind speed meters. Now you see that safety, reliability, efficiency, and simplicity are the core values on which the L100 wind turbine of Lachave Wind is built.
So nice, huh? You guys want to work on those things? Yes, we actually have a renewable energy course. So it's a part-time study course. If you become a journey person, you want to looking into that field, you can take the course to further your knowledge in that part. Yes, everything looks funny until you're standing on top of that tower. You will have all the protection, but still, usually they require 2 people or something, because even you have full protection, if you fall, you're hanging on there, they have to have a way to save you pretty quick. At that high, for sure, they're gonna swim. They're gonna swell a little bit here, there. Okay, so few things from that 2 video. One thing is, does all the wind turbine need a gearbox? Think again before you answer. Did you saw any gearbox on second video?
No.
No. E-fan. Oops. I think you need some kind of displacement. Okay. Second thing is, did you guys heard what they talking about that thing on top of the tower card? It called a nacelle. So the spelling is, I hope I can spelling them right. So that's the major part on top of the tower. It's called the nacelle. Those generators and hubs, everything is mounted on top, and they have a yard system. We try to rotate that. Okay, so that's two important things to get from those videos. A wind turbine is a rotating device converting kinetic energy of the wind into the electrical energy. Because when we're talking about turbine, we're always talking about a generator down there. I already showed you the video. Then the classification. That's the Canadian Electrical Code classifies how something is considered a smaller wind system, how something is considered as a larger wind system. So up and including 100 kilowatts, case the nacelle point turbine, the nacelle is the whole thing on top is considered the nacelle, and the yard motor is make the whole nacelle turning into the wind. Yeah, Milan is right. So large wind system have to be exceed 100 kilowatts. So that's a important number. You got to know them. Also, those wind turbine can be classified based on if the rotational axle is parallel to the ground, it's considered horizontal axis. If the rotational axis is vertical or perpendicular to the ground, it's called a vertical axis turbine. The horizontal turbine is the most common one. It have a high efficiency because those turbines can be set really high, really tall. You saw on the video, those are all horizontal one because they can set really high. Vertical one, usually you cannot get very high. The only benefit for the vertical one is it doesn't care which direction the wind came from. It will always rotate. And the horizontal one, you need have either active yard system or we have a passive yard system to making the turbine or making the blade facing the wind. But the horizontal one is the most common. They have a high efficiency. They can set really tall, so they get more power. Yeah, those are also you need to know them. Floating with anchored. So some of them will be, lots of those wind turbine will be mounted on top of the ocean. On the ocean, there's a benefit is because there's no obstruction to the wind direction. So because on the land, you might have a building, you might have a tower, you might have a hill, you might have a trees. Those will causing the turbulence in the wind, and they're also going to block some of the winds. So the new lots of those wind farmer is installed on top of the ocean. It's easy to get a constant wind. Most wind turbine generator are commercial, like a large wind turbine system. They are directly tied into the utility grid, and mostly are owned by utility company. So they can, those are clear renewable energy. It's much better than the traditional, like the power generation station supplied by coal or oil or natural gas. A wind turbine usually don't generate a very high voltage. One example is the GE, large GE turbine. They only generate at 690 volts. And they will bring that 690 volt go down. They have a transformer mounted at the top, then to step the voltage up to connect into the utility grid or use for the high voltage transmission line. Those conductor from top of the nacelle go to the bottom because you're using those vertical cable. You drop down, and when the nacelle is constantly turning to try to follow the wind direction, you will have some kind of control to preventing the over twisting of those power cable. So some of them, they have those limit switch to controlling how many times the nacelle have been turned. So if the cable become too tight, they will automatically stop the turbine to unwind. And also some have those PLC counters. They will counting the nacelle turning one direction, how many turns. If you reach the counts set by the program, it will also unwind, turning in the backward direction to preventing over twisting those power cables. Because the wind turbine, if you have a grid tied system, they have to matching the grid voltage and the frequency. So there's a different way to do that. And we know the speed of the frequency is of the generated voltage. It depends on how many poles in there and the speed of the rotation of the generator. The wind blow on the blades, they always, because you're not going to have a constant wind, right? So the wind speed going to change. So the blade might rotating at a different speed. So we have a different ways try to make sure the frequency generate or the voltage generate will always be matching with the grid voltage and the frequency. Some of those wind turbine generator, they call the asynchronous generator. So they basically is a square cage induction motor. When that motor, the rotor turning faster than the rotating magnetic field of the stator, it will become a generator. That's why they called them as an asynchronous generator. So they give you example, a motor have a, so the full load is 1750 RPM. That's when you use them as a motor. So we can figure out at 1800 RPM probably is the synchronized speed. So 1800 RPM, you probably have a 4-pole generator. And when this rotor is turning at a speed of 1850 RPM, this motor will become a generator. Let's see if we can go through the next page. Okay, here's an important idea. It's called a maximum power transfer. Okay, I'm going to explain this idea to you, then we can take a break. They said that maximum power is transferred in an electrical circuit when the load resistance matching the source resistance. So your source resistance is the internal resistance of the power source. Then when these two is equal, the maximum power is transferred from the source to the load. So I gave you some basic example to show you. We have a DC circuit, let's say a DC unlimited power source. Here's our load. So it's a 12 volt DC, have an internal resistance at 1 ohm, and we have a low. This low is 5 ohm. So in this case, we know the total resistance is 5 plus 1, 6 ohms. The total circuit current, 12 volts divided by 6, give us 2 amps. We know the load, the power, is equal to, let's say, I squared times R low. So 2 squared, 4 times 5, give us 20 watts. So when the load resistance is larger than that, we got 20 watts. Next one, we have the same power source, but we have a different load. So 12 volts internal resistance, 1 ohm. This load is 1 ohm. So now the total resistance is 1 plus 1, 2 ohms. Total circuit current, 12 volts, 2 ohms, 6 amps. The load power, IT squared times R low. 6 squared, 36 times 1, give us 36 watts. The third one, we're going to do one with a smaller low resistance. So same supply, 12 volts. Internal resistance, still 1 ohm, same power supply. This low, we only have a resistance 0.2 ohms. So this time, the load resistance is smaller than that. Total resistance, 1 plus 0.2, gives 1.2 ohms. Total current, 12 volts, 1.2 ohms, 10 amps. The load power is IT squared times R low. 10 squared give 100, 100 times 0.2 give us 20 watts. So you can see when the load resistor larger than the internal resistor of the source, you only transfer 20 watts to there. When the load resistor smaller than internal resistance of the source, you also only transfer 20 watts. Only when load resistance equal to the internal resistance of the source, you can deliver more power to the load. That makes sense? Yeah, so if you have to answer a question, you need to know which one to choose. You guys want a break?
So you said the higher the load resistance, the more wattage?
Did you say here? Which one have a more wattage?
You just basically want the load resistance and the internal resistance to be the same, right?
Yes.
Wattage up.
Yeah, that's when they have the maximum power go to the load.
Okay.
Did you guys want a break? Okay, let's back at 12:58. Don't be late. Okay.
Thanks, Jack.
Okay, see you. Hey, you guys back here?
Yep.
Yeah.
Oh, good. Oh, I can see Heidi. You got distracted there. Got distracted in my class. Oh, someone tried to show us a video. Dennis, what you try to show us? Your video's on. Okay. We continue. So a basic thing you have to remember here is for the electrical circuit, how the maximum power going to transferred. And when we're talking about in this wind turbine here, we're also trying to find the maximum power. That's when at a certain speed, at a certain torque, because the wind blow on the turbine's blade gonna cause that to rotate. That's the force and causing the torque rotating force, causing the blade to rotating. When it at rotating at a certain speed, they will give the maximum mechanical power to the rotor. But that part you don't have to understand too much because we will show you a little bit later. But you have to know the electrical circuit when the maximum power can deliver to the load. So there's different ways we can to get the maximum power from the wind. So blade pitch control is one of them, because in the video you guys can see those blades, they are not fixed angle. The angle can be changing, so make the blade either flat or totally vertical. That's considered blade pitch control. Variable pulley driver. So that's when they using those gearbox. They can have a different kind of ratio down there to make the rotating speed and the torque they get on the blade to deliver the maximum power. Another one they call the doubly fed induction generator. Is a different ways. So we're going to discuss some of them a little bit more. So here's some kind of drawing down here at the different wind speed. So this, if you look on the top picture, here the rotor's torque, and this is rotor's speed. So on different speed and at a different torque, here is the curve of your maximum power is not when you have the maximum torque. So if you look on this curve down here, the diagram, at this point, this is at 12 meter per second wind speed. The maximum torque is here, but the maximum power you get is not here, is down here. So it have to be in somehow the optimum torque and optimum speed will give you the maximum power for the wind turbine. So in here, the torque is the highest, but your speed only, for this picture, probably only 800 RPM down here. Your torque is 3.6, 3.7. On this moment here, your torque is at 3.1-ish, but your speed at close to 1200 RPM. So because we know the power, we learned in motor, right? Motor's power is horsepower equal to torque times the RPM over 50 to 52. You guys remember the formula? We're talking about motor horsepower. torque times RPM over 52. So to get the maximum power, you have to have optimal torque and the speed working together. In here, it's not we want this 1 ohm, is where this 1 ohm equal to the internal resistance. So you can put a different number down here, right? So in this example, I just use the internal resistance is 1 ohm. If the internal resistance is 2 ohm, then you want your load at 2 ohm. Does that answer your question, Case? Yeah. So you want the load resistance equal to the source internal resistance. That's where the maximum power can deliver from the source to the load.
Hey, Jack.
Yes.
This graph you're showing isn't the next page on the PDF. Where did you grab that from?
Yes, it's not in the PDF. It's I think the PDF today they might not update the PDF, but don't worry about the graph. This is one thing is I try to explain to you down here. So I'm not gonna test you on this graph. I just try to explain something down here is the maximum power you're gonna get is not at a maximum torque point or at the maximum speed point.
Right.
It's
Okay.
somewhere in between there. So
Gotcha.
they call that the optimum torque and the speed. We give you the maximum power. Another thing is try to explain to you is at a different wind speed, you can see that 3 meters per second, 4 meters per second. At a different speed, and if the wind is at 3 meters per second, your maximum power is down here. 4 meters per second wind speed, 5 meters per second. You can see that a maximum power point is moving. So in here, this is the mechanical power with speed. So your maximum power point at a different wind speed, it also changes. So your rotor rotating speed will also have to change, and your mechanical torque also have to change to give you that maximum power. Here, that's the basic idea. It's good. That's why when we're talking about the why the wind turbine, the rotor blade, they have to have the pitch control, because if you at a certain wind speed, your rotating speed need to be changed, and your blade angle changes to get the optimum torque with the speed working together to get the maximum power. Here's something, if you want, you can take a picture of this slide, but the major thing on here is I want to show you something down here is, let's take a look at the 4 meters per second. So 4 meters per second, yeah, it's hard to see. Let's say 6 meters per second. So it's the 1, 2, 3, 4, the fourth line, 1, 2, 3, 4, this line. At 6 meters per second, you have a power. So they said the maximum power you can get is, if you guys look in my mouse down here, it's close to 50 watts, right? And at the 12 meters per second, this point is really close, because the machine have some efficiency issues down here. it's really close to 400 watts now. So here's something I want you to remember or to know is the available wind power with wind speed. The relationship between them, we look at 12 meters per second is close to 400 watts. At 6 meters per second, it's close to 50 watts. What type of a relationship they have? So when wind speed double, the power is 8 times. So it's 2 to the power of 3rd. That makes sense? Yes, no?
If you double the wind speed, you're going to get 8 times the power.
Yes. But the relationship is, here's your double, so 2 times, your power gonna be 2 to the power of 3rd, right?
Right.
So if I ask you a question, I said, here is if my wind speed increase from 4 meters per second to, let's say, 5 meters per second, the power increased how much? So the calculation will be like that. You go 5 divided by 4. It's a 1.25. 1.25 to the power of 3rd. It's a 1.953. Make sense?
Yeah.
You all know how to do this calculation? Hayden, you better remember it.
Don't quote me
get
on
it.
it, but yeah, I think so.
If you get this type of question wrong,
I'm going to get hurt real bad.
yes. And one more thing I want to say to you is last time you said, can you take some notes for Peggy, right? You said Peggy because he lost power or lost internet.
Oh, that's
Peggy
not
got a better mark than you. How you get that?
That doesn't surprise me.
So someone asked me to go over again. So what you do is if your wind speed changes, you first find out how much they changed. So if you go 4 meters per second to 6 meters per second, right? Your calculation is going to be, the one before is a 5 divided by 4, power of 3rd. And this one, your power going to increase. What you do going to be 6 divided by 4 qubit. That's the thing. If you know me from before, yeah, in my class, and they call me the mean Asian because certain things they said a Caucasian instructor like this probably not gonna say to you, especially on the in your face and in front of the whole class. But I'm a mean Asian, so and you made those kind of mistake, I will say to your face. Hayden, if you can't handle it, send me an email. I will apologize to you.
No, you're good, Jack. I appreciate it.
I think those things called motivation, right? Have to push you to study hard a little bit more.
Yeah, exactly.
Okay, so from this one, all you have to understand is the relationship between the wind speed and the available power down there. Okay, you're gonna get a test on it. You better know it. But this drawing didn't tell you that, so I gave you the relationship. The generated, this is not the generated rating. It's this diagram tell you at a different wind speed, what's the maximum available power you can get from there. This calculation is called the relationship between the available wind power to the wind speed. This is not even we talking about the generated power. It's just the power available, that mechanical power available in the wind. Answer David's question, the case question? Yes, no? A good case? How about Dave? David, you okay? Okay. So if you ever forget the relationship, I hope you're not forgetting them, but you can take a picture of this one because all you have to know is the speed with the available powers relationship. You're not gonna design in the wind turbine. You're not gonna be try to figure out how to get that. It's automatically done by the manufacturer. On each torque speed curve above, the diamond shape, they indicating the optimal rotor torque and the maximum amount of mechanical power at the wind turbine. That's also diamond shaped on there. The rotor speed, maximum mechanical power. Wind turbine varies with the wind speed. So if you look down here at the different wind speed, and this maximum power also shift go along with at a different speed. So it's not always constant at this speed or that torque. It will move around. So this is performed automatically by a controller in the wind turbine. That's why we said you need to understand the basic. Next one we're going to talking about, they call it doubly fed induction generator. In year 3, you guys learned about thing called motors and the generators. Mainly you learn the motor, you learn the scam, you learn the round rotor motor, you learn the synchronized motor. This doubly fed induction generator is kind of like a round rotor motor. This round rotor motor or round rotor motor, my pronounce, it's really hard for me to say this word, right? You guys, as long as you understand this. The difference between this and a scam scheme is the round rotor motor. We have a secondary circuit, right? They have the rotor winding goes through 3 slip rings. They can connect external resistance when you learn this motor in third year. But in here, we're going to try to do something is we try to, when this rotation of the blade causing generator rotate at a different speed, we want the connection to the grid have the fixed the voltage and the fixed frequency generated. So to understand that, I will try to show you something is we use a converter down here because here's the grid. The grid, let's say we have 600 volts, 60 hertz. To make this generator always generate 600 volts at 60 hertz, even when the speed of the wind of the blade is changing or the rotor rotating speed is changing, we are using a connection onto the rotor part. We first using this converter is more like a VFD. Some of you learned VFD in third year, some of you didn't. This is going to be first converting, have a rectifier part to changing this AC into a DC. Then they're going to invert this DC back into AC at a different voltage, different frequency. This different voltage at a different frequency going to connect onto the rotor winding. So by using a different voltage, different frequency, current or voltage feed into the rotor winding to matching with the rotating speed of the rotor, we can always generate 600 volts and 60 hertz at the stator part. That's what we call the doubly fed or doubly fed induction generator. They have a pretty high efficiency. Another major advantage, you probably don't have to know it. We're talking about different ways we can get this fixed voltage and the frequency, but this one, we can use a smaller inverter down here. A different one is we don't use this doubly fed induction generator. We let this wind moving the turbine at a different speed. Then this generator rotating at a different speed, we can generate, we call a wide ACs. It's maybe you generate a voltage at 400 volts at 30 hertz, or when the wind speed changes, you might generate 500 volts at 50 hertz or whatever the frequency. Basically, we don't care what's generated. We just put a kind of like a VFD inverter down here. We converting that AC into DC. Then we inverted the AC back into AC to matching with the grid. So that's different way you can do it. But if you do that way, you have to use a bigger inverter, because that inverter, it depends if you have 100 kVA generator, your inverter have to be rated 100 kVA, or large, you might have to overrate your inverter a little bit. But this way, even you have 100 kVA generator, this inverter, you probably can just use a 30, 40 kVA inverter, because you're only feeding a small amount of current into this rotor circuit. So here's a more detailed picture. This is the induction generator. That's what we call the doubly fed induction generator. The voltage is generated on the stator part. The stator part is connected onto the grid. And the wind gonna push this turbine. We have a control down here. We can control the pitch of this one, but still, this turbine will rotate at a different speed, so this rotor will rotate at a different speed. And it based on the rotating speed of those turbine or the blade, they're going to be have the grid connect AC first, rectify into a DC, then they invert it back into AC. They feed this AC into the rotor. So this AC feed into the rotor is matching with the rotating speed down here to keep the constant voltage and the frequency generated on the stator part. Another one called a blade pitch angle control is we're talking about those the video showed you those motor inside the nacelle. They control the angle of those blades. This is called blade pitch control. The blade pitch control is if you have a too high wind speed and your turbine might turn in too fast, it can cause damage to the whole machine. So you want to make the blade almost like a parallel with the wind. I might have a picture to show you. Just give me a second. So that's when the blade, if you want to get the wind blow on this blade. So here's your blade, the shape of the blade. So when this wind blow on here, you're gonna push the blade to move. But if this blade, they kind of go, they can rotate. So the way how they rotate. So here is almost rotate to the flat. So when the wind blow from this direction, and the blade is now gonna face in the wind. So if they go totally flat to this 90-degree, the wind gonna just pass in from the top and the bottom. You're not gonna push the blade to rotate at all. That's considered blade pitch control. The blade pitch control we're using in field, one way is you try to control the rotating speed of the blade. You can use that pitch control because it depends on which angle you set. You can catch more winds or catch less winds. But we call the feather, the blade feather is if the wind speed is too high. So if that blade start rotating, you're going to damage your machine. That's you're gonna feather the blade. Feather the blade means put the blade at 90-degree. You don't want any wind to blow on them. Another one is when you first try to install them. So when you try to install those things, you think you have a crane, try to lift them up. You try to have people walking around them do you want those blades ever got pushed by the wind? So during the construction stage or during the maintenance stage, you always want the blade feathered. So high wind, that's one thing. Construction and maintenance, you always want the blade feathered. Okay, so that's important to know when you're going to feather the blade. Here talking something is how this duplicate fed induction generator, if you put in different frequency AC into the rotor, and you can always generate a fixed frequency at the stator. So to explain this, they try to say, if you, let's say, if you guys can see that on a piece of on your D2L document. So we have a 6-pole generator. We want to get a 60 Hertz from the output of the generator. So we know the speed will be 60 times 120 over 6, right? So that will give us 1200 RPM. You guys learned this formula in second year, and you'll be using a lot in third year. So if my wind speed now gonna move in this one, let's say for a normal generator, if it's a normal, like say, called a singly fed generator, if my wind speed or rotating speed, don't call it wind speed, rotor speed is at 1100 RPM. So I can calculate the frequency will be 6-pole times 1100 RPM divided by 120. We give us number. You're only going to generate something at 55 Hertz. So we cannot use this 55 Hertz to connect onto the grid, which is has 60 Hertz. So the way the W-fed generator, what they're gonna do is they're gonna put a 5 Hertz AC signal into the rotor. So here's what they try to show you. If your rotating speed, the mechanical coming to push this in, that's the rotor speed. But we require a 60 Hertz down here. That's equal to the total of them. If this one wasn't rotating at that fast, I can put an AC signal to make up for that 5 Hertz. So the 5 Hertz, we're rotating at the same direction, creating a rotating magnetic field, rotating in the same direction as this rotor rotating. So the stator will generate that 60 Hertz. What if the mechanical power to push in this rotor rotating too fast? So if the rotor speed is at 1300 RPM, so your frequency will be 6 times 1300 divided by 120. You will got 65 Hertz now. So your speed is faster than the normal speed. So what you're gonna do is you are going to be putting AC signal into the rotor, but this time is creating a rotating magnetic field in the opposite direction. When you're creating that in the opposite direction, you're gonna cancel some of that fast running speed for the rotor. So you're still gonna generate that 60 hertz down here. I know some of you, because from my last class, I know students have a difficulty to understand this. But let's say this. If we have a really long train, so this is a train. This train is moving at, let's say, driving really slow, 10 kilometers per hour in this direction. So if I have a pulse down here, here's a pulse. The relative speed between the train and this pulse is at this 10 kilometers per hour, right? Then I have a person. So this is the train going in this direction, 10 kilometers per hour. My pulse is here. The train related to this pulse is at 10 kilometers per hour. I have a person standing. The person is on this train. The person also walks. The person walks at 5 kilometers per hour. If the person's walking the same direction as the train, so what's the relative speed between the person and the pulse? 15 kilometers per hour. That's right. Because the trains are moving at 10, your person on the train also walking at 5. So now the relative speed is at 15. What if this person, the train is still 10 kilometers per hour, the pulse is here now moving, but the person is walking backwards at 5 kilometers per hour. So now become a 5 kilometers per hour between the person and the pulse. If you understand this, this is the same idea. You try to create the relative rotating speed between the rotor and the stator, so we can use the formula F equal to P times N over 120. Okay, so even if you have a difficulty, did you guys have this one in the PowerPoint? Because I think they copied this from a different course. No, this one wasn't in the PowerPoint. Okay, one thing is I could update the new PowerPoint on there. Another one, people also tell me, they said this formula, when those number on there, then it's kind of slightly different than what you guys learned before. So I'm gonna give you a new formula. The rotor frequency equal to the gray frequency, or the network frequency they call it. Subtract number of poles times the rotor RPM over 120. So F rotor is the rotor AC frequency. F gray is the gray or we call the utility gray AC frequency. P is number of poles of the generator. R rotor is the rotating speed. Speed of the rotor. 120, you guys know, right? You need a pair of poles, and you have usually this is RPM, so the frequency is related to seconds, so you need to divide by 120 to get that. The negative frequency is if you're looking at that PowerPoint. Or I can answer you this question is, we have a three-phase motor or generator, right? When you learn the three-phase motor, we try to creating rotating magnetic field. Rotating magnetic field. If we put in A, B, C frequency, then we cause the motor, the rotating magnetic field to go clockwise. If I put in A, C, B frequency, how this rotating magnetic field gonna go? Counterclockwise now, right? That makes sense? So this is gonna be the formula. Did you guys get this one right down? I'll take the picture. You need it. You will have a, yes.
The only thing I'm a little confused on is that in order to get the rotor, like, it's just for the rotor frequency and the grid frequency, like the rotor frequency is equal to the grid frequency minus the number of poles times the rotor speed over 120.
Yeah.
Okay.
So when you guys write this down, or you take a picture of this down, we can do some examples.
Okay.
To make you understand better. Can I flip the page? Yes, no?
Yep.
Okay. So let's say in North American, the frequency of the gray is always 60 hertz, right? We have a double-fed induction generator. It's a 6-pole generator. And if the rotor speed is, let's say we do it before, 1100 RPM. We want to find the frequency of the rotor. So you go frequency of the rotor equal to 60 hertz, subtract 6-pole generator, 1100 RPM, divide by 120, that will give you 5 hertz. So your rotor need to put a 5 hertz AC connect into the rotor, and because it's a positive number, so you need to make that rotating magnetic field rotate the same speed as the rotor rotation.
So you initially got the 55 or whatever, and then you just went
Yeah.
60 minus 55.
Yeah, 60 subtract 55.
Okay.
Or if you want me to write the whole thing down.
No, you don't have to. I just wanted to make.
Right, so this part equal to 60 subtract 55. Sorry, I shouldn't be skipping the step because it's teaching, right? Or that's question 1. Question 2, what we're gonna do is same gray frequency, 60 Hertz. We have a double-fed induction generator. Let's call this one, this time we have A poles. The rotor speed is at 1,000 RPM. So we want to find the rotor frequency. Still same, 60 Hertz. Subtract A times 1,000 divided by 120. 60 subtract, I'm going to give you a number. 66.7 Hertz. So your rotor will be negative 6.67 Hertz. If I just use 1 decimal point, yeah, so case you got, okay, you need to use 6, subtract that. So you're left with negative 6.7 or negative 6.67 Hertz. These two numbers both okay. Yeah, because this portion already gave you this number. You got to use 60 to subtract it. Yeah, so those are the speed of the mechanical rotation. Usually it's always the speed of the generator. Unless, because it depends on this setting up. If you have a gearbox, you might, the blade is rotating at a much slower speed. If you don't have a gearbox, your blades directly couple onto the generator, then the blade speed will be the same as the rotor speed. But when we do those type of calculation, is always the generator, the rotating speed or the rotor speed of the generator. So pretty simple calculation. Yes, no?
Yeah.
So you probably will have one question you have to do this calculation. Yeah, one question of 50. But a mark is a mark, right? If the negative number, which means look at this picture, the positive number means this red is the rotating magnetic field. So your AC put in there, this is the positive frequency. We're causing the same rotation direction. Negative number means you're causing the rotating magnetic field is in the opposite direction as you actually the rotor direction. That makes sense?
I don't want to say yes and then get it wrong on the test, but yeah, it makes sense.
Yeah, because it came from an inverter, right? So the inverter, basically these things automatically does by that controller. The controller, we send out the AC signal in either you have a phase sequence as ABC or phase sequence as ACB. Okay, I'm not gonna ask you too deep in this thing. All you have to know is, can you do this calculation? If you're able to do this calculation, you came out with a number, it doesn't matter 5 hertz or negative 5 hertz. That's all you need to answer. You don't need to worry about the negative number means or positive number means. Then, is this formula important?
Yes.
Yeah, so you better know this formula, better write it down, or when you do the exam, you have this formula ready, because yes, you're gonna do a calculation with this. Now, whatever, yeah, 2% important. We're not gonna ask you it's clockwise rotation or counterclockwise rotation. All you have to do is give me a number. And like you guys ask, clockwise rotation or counterclockwise rotation in those type of questions have no meaning. It basically means, are those two in the same direction or are those two in the opposite direction? Well, okay? Yes? No?
Yes.
Yeah, you better okay. Otherwise, you're gonna lose that 2%. All you have to know is you know how to do the calculation. Okay, this is the formula they gave in. It's the same thing, but they just they use different things. They use n to represent the poles. They use this smaller n to represent the RPM. That's why last class people ask me, oh, that's not the way you learn in the apprenticeship. So I gave you the one as I'm writing them down. Yeah, opposite direction is negative. But lucky you don't have to remember what's the opposite or positive direction means. All you need to know is you know how to do this calculation. In the real world, it matters because the positive and the negative again causing that you want to get that 60 hertz. That's why if the wind speed is too fast, you want to give opposite direction. If the wind speed is too slow, you want to give positive direction. So here is a different way to do them. You have prime mover, that's the wind pushing the rotor to rotate, and then you're going to generate a voltage down there. Then if you're using you're gonna rectify that generated voltage, and you're gonna invert that rectified DC into AC. That doesn't matter now. But here is one thing I want to remind you guys. So here is a wind turbine generator. Doesn't matter you have the gearbox or not. So I guess later on they will show you that. Here's your generator. Come out. You have a AC, DC. We usually call that a rectifier, right? You're gonna converting this AC generator down here into a DC. Here's your DC bus bar. Then you're gonna put a DC AC converter. This one we usually call it the inverter. So now after this, you're gonna have a standard. Whatever the frequency voltage required to connect onto the utility power grid. So this is a very good, or you almost can call the best solution. So then doesn't matter how fast or how slow this make the generator rotate. As long as you generate something, you can always rectify it to DC. Then you can change it into AC. So this portion down here is like you learned if you've been in harmonized class, that's almost like a VFD, right? You just have to using a large size VFD to do that. So this will be the best solution. You might gotta ask you a question, which one is the best? So you convert into DC, convert back into AC, that's your best solution.
Sorry, Jack, that's just the regular double-fed induction generator, isn't it?
Then for this, you don't need a double-fed induction generator. You can use any type of generator. Mostly, you will just use a single-fed. So for this, you can use any generator. The one we explained to you, the double-fed induction generator, it have those benefits, but the control is much more complicated. You have a constantly monitor. If I show you the picture down here. So you can see for this one, you have to constantly monitor the speed of the rotation, and you have to constantly make adjustment to generate a AC frequency voltage down here to matching with the rotation down here. So this control is much more complicated. The only good thing come with is this AC DC AC converter can be a smaller size. Why they using this thing in the wind turbine is you guys saw the video in there. Do they have a lot of space inside the wind turbine?
No.
No, right? Because usually they don't have a lot of space in there. So in order to using the one I'm talking here, so this is you can call AC, DC, AC converter. So basically they including two parts, rectifier part and the inverter part. These need a bigger size. If you have the room, you can put this bigger size in there. Your control is much more simple. Maintenance is much more easier, and you have less component in there. But if you really, you need the space inside, you don't have enough space to put that bigger this converter in there. Also, when the converter become bigger, it also the price goes higher. Yeah, so they call this one, I think they have a name. I think they basically call three-phase rectifier and inverter. That we consider as the best solution. Just because we don't have enough large enough room in there. And the manufacturer always try to save money. They don't want to spend lots of money to buy this thing. So they will use those doubly-fed induction generator to save the space, use a smaller VFD type of thing. Okay, we close to the end, but we can continue tomorrow. So you guys know tomorrow we use a different link, right? Yes, no?
Yes.
Yes, yeah. And tomorrow we start at 8 o'clock, right? Don't be late. If you're missing anything, I cannot help you.
You mean different link, but the same like one on the main page that we clicked today, right? Like just use the different.
So
it's not under content, but under course home, I think, right?
Yeah, under course home. So tomorrow you're gonna click this link, right?
Yeah.
Oh,
right. June 11th.
Yeah.
Okay.
Make sure. Yeah, all the link is already posted. Make sure do those online quizzes, and if you have difficulty doing the online quizzes, you gotta go through those Scrum learning. And also, if you have a time, because you have to make time, you gotta starting on those working sheets. The first one is the wind power. So because you still got a weekend in there, but there's still a lot of material. You got to study hard. Don't make me show you the ruler. Okay, if you don't have any question, I will see you guys tomorrow. If you still want to ask me something, you can stay here. You're welcome.
Yeah, hey Jack, you said quizzes. I only see the one quiz and then the actual test on quizzes there.
Yeah, the one quiz, every time I think they give you 10 questions randomly.
Yeah.
So you can try multiple times.
Oh, just keep doing that one quiz over and over. It'll be different stuff.
Yeah.
Okay.
The best one, you can call them three-phase rectifier and the inverter. The name is not important. I think probably on the exam gonna call three-phase rectifier and the inverter somehow related, because it's not really called VFD. The VFD is called a variable frequency driver, so they're not gonna call that. The VFD is used for the motor to control the motor speed. That's where we call the VFD. This one probably going to call three-phase rectifier and the inverter. So they might throw you different options. They say, oh, we can just control the use a gearbox to change in the speed or something to keep the generator, the voltage and the frequency steady. So that probably not going to be the best solution, right? Yeah. So if you don't have a question, I will see you guys tomorrow. Yeah, Hayden, I still believe in you. So the first one, I will say, you might be encounter some kind of problem, or you might have a difficulty, but don't let me disappointing in you on second exam. I always give people second chance. Good. I like you. That's why I like to joking with you. You're welcome. Yeah, last time I said you got the bonus because you always answer my question in the class. No pressure. Yeah. Just do your best. Okay. Yeah, see you tomorrow. Anyone else have any questions? Parker, God bless. God bless you. Yeah, bye.
Thanks, Jack. Bye-bye.
Yeah. You're welcome.
Hey, Jack.
Yeah.
You don't like the vertical axis turbine?
It's not I don't like them. It's they are not so popular because they cannot install very high, and when they install close to the ground, and the ground you always have like trees, houses, buildings, or hills. They will affect the wind power they can get.
What if it's higher above then? Like higher up?
No one builds those in really high. I think they have a technical difficulty to build them really high.
Okay. It just looks like it's more reliable. Like with no need for extra motors to make it turn anything. Just it picks up wind from all directions.
That's the good thing, but the worst thing is those commercial one, larger one, nobody ever built them vertical one.
Okay, cool. Thanks.
Yeah, I guess if you ask me one more thing, I probably can say why people didn't build them really tall is they cannot handle very high speed wind, because when you go higher, the speed of the wind gonna go really high, so they're gonna rotating like a crazy. I didn't say it's really very relevant to IP. I think we said you're gonna have a few questions, like a 4 to 6 questions on IP relate to this topic. The most IP question is still going to come from the code. Yeah, usually the IP we have a few questions here, a few questions there, but mostly is come from the code. I don't think you're gonna encounter. You might encounter 1 or 2 maximum automated controls. Usually I didn't hear people said question on automated controls on IP. Any other question? If not, I'm gonna end the meeting. Going once, going twice. No. Okay, I will see you guys tomorrow morning.